Okay, hello, welcome back. Today is 1st of March to 2025, and I'll be doing this stream, recording session, video logging, because my YouTube channel got removed because of some nudity issues. I know it's embarrassing, but well, there's nothing I can't do. Well, there is nothing that I can do if Google Chrome ads show nudity while streaming. It wasn't actually nudity either. It was just some weird content that they keep showing me. Anyway, well, it's good to get the embarrassment out first. So I'll be doing these recording sessions so that I have and try to remember what I said before on the live streams, and hopefully, if nothing is wrong, I can upload these recordings again onto my new channel. Yeah, that's that. Today I'll be going over the very first notebook, Jupyter Lab that I did when I started looking into genetic algorithms, and because it is the very first, it's the notebook is named GenAlgo 0. Yeah, it's Python, so you start from 0 when it's actually your first. One sip of decaf coffee. So, as I said before, we've already established what the answer is when given these conditions, these items, these utility values, and these constraint values. And the answer is 710. I forgot which exact items that included, but just it's not that important. In the future, I might have to make random. I might have to make a function that generates the random items, and along with the random utility values and constraint values, and so that I can generalize the problems a bit further. Cool. So I run that. I run all these values. These values are the same from before when I was trying to figure out the answers. The random gene generator, although I don't use that these days, because I don't use the random gene generator, because I like to start with zeros, or what I came to call void lists or void genes, because they're empty, they're void, there's nothing there. As well as it's not exactly void either, because the definition of void is the absence of absence. So the absence of even the absence of something. That is what the word void means. Anyway, and the mutation function is still the same. Hyperparameters is still the same. Max constraint being 4,000, so if it goes above 4,000, it's out. Population size is 500. Number of items, again, is 20. Mutation rate is 3% or 0.03. Crossover rate is 0.7. I don't think I use that right now. And generations, max generations, or the number of generations to evolve for, is 3,000. skip all this bit because this was where I practiced and tried out the code. So what I'll be doing is just did I random? Yeah, I did. Actually, I have to correct myself. In this notebook, I do use a random gene generator. Random gene generator, yeah. And I don't use the void genes, so that's okay. Okay, so random gene generator, and what this does is generate how many? 500 genomes, 500 entities. 500 entities that are 20 items long, 20 elements long, and start that off as use that as the genesis pool. Use that as the initial population. So now that I have the initial population, I just want to maybe try calculate the summed utility values or the fitness value for each entity, and so far the max is 670. So it's not bad, but it could be a lot better since we know it's 710. No, don't run that again. And the constraint value, summed constraint value for each entity is 4,970, which is way above 4,000. So whatever that one was, it is going to be eliminated. Sad. And if I use the selector, which removes entities that are above the weight threshold, that is 4,000, and 41 were eliminated because there were 500. Now there are 459 entities. So that was a test run for like first thing. So let's just start the evolution. We put the initial population into a variable called the world, and then we run it for 3,000 generations, where and within each generation the summed utility values of every entity will be calculated, and yeah, actually we have the initial population pool, and then we use the function selector to sift through and remove the ones that go above 4,000 in weight, and then we put that in a dictionary called entities dictionary, ENTTS dict, and for each dictionary we calculate the summed utility value and use that as the key when being used as input into the dictionary, and the entity will go in as the value. So key is the summed utility value, and the value is the entity that has that corresponding summed utility value. And then we calculate, and then we count how many entities we have currently, and calculate the number of new entities to procreate or generate through procreation amongst the entities that are selected from the remaining population of that generation. And in this, I'll talk about how to select the parents for procreation in later videos, but yeah, so let's leave it at that. So what happens is, what usually happens is that entities with higher summed utility values are more likely to be chosen as parents. So that's that, and then we create new entities depending on how many we need, how many new ones we need, and then add that to the world, which is the remaining population. And then if it goes above 500, we just cut it 500, and yeah, and then towards the end mutation goes through for every entity in that current generation, and then at the very end of each generation, the selector function does this job again. I could probably remove that, but anyway, the selector function does its job again to eliminate. I don't like the word eliminate. Remove. Take out. No, that sounds like Hitman. Anyway, I need to find a new word for that. It doesn't sound nice. It sounds a bit derogatory. Yeah. Anything above 4,000 has to go, and then the next generation starts all over again for 3,000 times. So let's run it. I wonder how long that's going to take. Probably like 12 seconds. Because Google Colab is 3 to 4 times slower than my MacBook Pro. So we'll just have to wait and see. It's very slow. We are in the 2600s, 2700s, 28, 29, 30, 100. So that's done. How long did that take? It took a minute. Okay, so that should take about 20 seconds. It's an estimate, so I might be wrong. And so now that we have the world after 3,000 generations, we can run that to calculate the summed utility value for all the entities, and then sort it in descending order from max to min, and let's have a look. So in this case, 615 was the best, which is bad because it's not. It's just normal. It's like very average. It's not average, but since we know it's 710, it's not that good. It's not that promising. So let's try that again. Let's try that again, where the best one right now is 705, but that probably weighs 4920. Could be wrong, it could be some other entity that weighs that much. So 39 were removed. Yeah, Genesis is still there. So let's run it again. Well, this will take a minute again. So it shows slight signs of promise, but a lot of room for improvement. And well, I know that because I know the answer. I've done more work after this, so I'm actually speaking after the fact. So maybe that's not fair. Maybe you could say that I'm cheating. But yeah, for now, that 615 wasn't so good. It wasn't good enough. I mean, it wasn't worth 1 minute of this. And I know that a lot of the processes that I'm doing right now could be shorter in time if I coded everything correctly in more efficient manner. But I'm not. But I'm just testing things out, so I care less about that for now. 660. This time the best one was 660. So last time it was a bit unlucky. Let's try again. 660 was the best. Yeah, I just realized. I just said 660 was the best, which is true, which is right. But I also have to consider what I mean by best. And to do that, to know what I mean by best, I need to know what I mean by good. Because the words go good, better, and best. Good for the problem, good for solving the problem, the knapsack problem, or the backpacking problem, backpacker's problem, knapsack problem. But is good really good when you think that I want to use this for some other complex problems where good suddenly means okay, normal, and therefore what used to be the best yesterday could now be just, better than average today. Or even worse, what used to be good today might not be so good tomorrow. And what was the best today could actually be very, very bad tomorrow. So things change and problems change. And context changes as well. So that's a thought for later. Food for thought, but for later. But it's definitely something that I should think about, because you don't really know what is good. Could be good now, but think about it like this: you might not want to pack more than 4,000 grams for kilos, like in this problem, given these conditions. But what if packing for more than 4,000 grams, 4 kilos, was actually a lot better for your health? So maybe we shouldn't remove entities above 4,000. No, these things can change. These things are so arbitrary that they can change over time. So right now, for the very last one, it's still 650, so worse than 660, lower than 660. I don't want to say worse. Let's try one more time. I know these are bad because I know these are low because 710 is the highest you could go. burn. That rhymes. That actually rhymed. Low and go. But it'd be nice if for some, during one of our attempts, we could get something close to 680, 690. Right, done. Yeah, so it takes about a minute. 670, yeah, a lot better. Somewhat better. Maybe one last time? Okay. I mean, I have to keep in mind that it's been 21 minutes since the start of this recording, and I still haven't come close to 710. And when I know that by brute force iterating, I would have had the answer by now. I would have had the answer, gone out for coffee, and then come back, and then just sat in my chair, relaxing for the past 5 minutes. So far, this is not worth my time, strictly speaking, in terms of the efficiency of this method when working with 20 items. $6.50. Maybe third time's the charm, but maybe the last time is the charm, or the charm is the last time. And while this is running, another rant that I could go with is, I think machine learning and any kind of algorithms are fun if you don't know what the exact answer is. But once you know the answer, everything becomes meaningless. But therein lies the reason for this too. When the problem is so complex or so huge, when the space is so huge, it becomes almost impossible to get the truth, the true answer. And that's when you have to start estimating, when really good enough is good enough. When you accept the fact that the true answer, what the true answers are just impossibly hard to get in terms of this. 650. I mean, but I have had occasions where I got 695 by doing this, 680, 675. What? How many times have I run this? I think this is the 6th time now. So running for the 6th time, definitely longer than brute force iterating, but I'm always curious. Well, not so curious now because I know the answer, but yeah. done. 6:35. That's even worse. So I think I'm gonna have to end there. I don't know how long I'm going to have to go through this, but yeah. I mean, I know ways to make this a lot better, but I don't think I should do that in this video. Okay. That's it for this recording. Well, thanks for watching. Love you. Bye.